time, where we had the metric in terms of, let me just write this now as in Roberto's way of writing the metric of with some function here that we get to specify, but this is manifestly spherically symmetric, where the sphere is this sphere, rho is a coordinate that is a radial coordinate, so rho equal to 0 is the tau axis, and rho equal to infinity is the boundary of the subcan, with, in this case, f of rho is just 1 plus rho squared over L squared, where L is the ADS length. So this rho equal to L would be, roughly speaking, sort of halfway to the boundary in a set of coordinates where really what I am plotting, the sort of a blackboard metric would have been 10 of rho, where you can write this metric a little bit more easily as 1 over cosine squared times just a metric which has a manifestly sort of flat form in spherical coordinates. Okay, so this is like rho equal to L, rho equal to 0. And we also talked about Poincare ADS, where you really take a single patch that's, you can think of in some sense causally as generated by, a set of space-like separated points from one point on the boundary. And if you do that, this patch limits to a flat boundary metric. So the Poincare ADS, the Poincare patch, gives you the Poincare metric that looks like, I use the z coordinate, so L squared over z squared. Again, we have the same length with minus dt squared plus dx squared plus dz squared. And what I wanted to fill in from last time, because I forgot whether I said it or not, this boundary, which is at either rho equal to infinity or z equal to 0, is really endpoint of future-directed null geodesics or past-directed null geodesics or space-like geodesics. So really the boundary is both what did Malcolm call it, SPI, as well as scri plus and scri minus. Okay, because all of these geodesics end on this. So scri in this the null infinity is time-like, and that's so the null. This delimitation that it's a spatial infinity or null infinity, that just pertains to what is it an endpoint of, whether it's endpoint of space-like geodesics or null geodesics, or I plus and I minus would be endpoint of time-like geodesics. Well, here I haven't compactified the time direction, so this really runs off infinitely far in this picture. If I had compactified it into, let's say, a teardrop shape, I would have seen the I plus and minus as well. Okay, so that was one comment that I think I didn't get to mention last time. We were talking about, we ended with talking about the scale radius duality, which was the observation that the UV, so maybe I should write that from last time. So scale radius, or also known as UVIR, correspondence or duality or whatever. I think correspondence is a much better word because I really want to use duality for something that's really describing something physically equivalent, whereas here it's just part of a map. It just says that effectively the UV cutoff in the field theory corresponds to an IR cutoff in the bulk. And in particular, if you have, well, let me now draw the sort of the Poincare coordinate picture, because that's where it's realized. So this would be the z direction. This is one of the x directions, and I'm taking it at, say, t equal to 0. If you have some excitation at some value of z, let's say z equal to epsilon, then in the bulk, okay, so this is, let's say, if epsilon is small, this is epsilon over L is small, then this is very near the boundary. On this diagram, it would be, let's say, somewhere here. Then what you expect that excitation to be described by in the CFT is, well, there's not much going on sort of in these directions, so you don't expect to excite much here, but you expect that somehow the knowledge of what's happening here is somehow encoded in the field theory in something whose scale is also, roughly speaking, like epsilon. This is very heuristic. As you go towards the boundary with this bulk point, then you're really, well, it requires a high energy to stay put here, because as we saw, the geodesics would bounce off, and you only need, none of the time-like geodesics make it all the way to the boundary. It's only in the infinite energy limit that you could actually make it there. So the intuition is this: if you want to be right up at the boundary, you're really at the full UV scale. And conversely, if you want to be deep in the bulk, somehow describing maybe the same particle, but now deep in the bulk, in the CFT, that must be described by some, by some large, well, by information that's contained in a large region in the CFT. So that's sort of the intuitive phrasing of the UV-IR correspondence. Okay, let me pause and see if there were any questions on any of that we did last time. Okay, so another element, so I'm going to now skip what one usually does, because as I said at the beginning, there's hundreds of hours of lectures. So typically people develop, the spectrum of the two theories of the two sides matches, and if you have excitations, they match on the two sides. The interesting regime from GR standpoint is when you start getting something other than ADS. So since the Newton's constant goes as the string coupling squared, that goes as 1 over n squared. Okay, so you really need excitations of order in the CFT of order n squared to start actually deforming the geometry from ADS to something that's just asymptotically ADS. And we'll be seeing examples of that in a moment. But let me just say that, if you want to probe some physics just in ADS without deforming the geometry, you can ask about what sort of observables you might have. You can calculate expectation values of various operators, and what that tells you is a fall off of bulk fields. So there's a operator state correspondence where you have a where you would have so in the CFT, let me do CFT in bulk. You can measure only sensible physical sort of gauge invariant operators. And so such an operator has a corresponding sort of bulk field. So if the operator has dimension, scaling dimension delta, the bulk field has a mass. And there's a relation between the mass and the dimension. So m squared over L squared is like delta times delta minus the number of dimensions. So let's say if we're back in the, I'm now back in sort of the ADS5 plus CFT4 context. So if you excite, so if you look at a, fall off of this field in the bulk, you can think of, so this in the bulk, as you go towards the boundary, this field falls off as with a characteristic polynomial law as just some coefficient over R to delta. And if you then measure the corresponding operator, the expectation value is read off from this coefficient of this fall off. So, and one of the important examples is when you have, when you're exciting the bulk metric, this is going to correspond to the stress tensor on the boundary. Okay, so you might have a some, so you know that if you have, let's say, Schwarzschild metric, you have asymptotically flat region, but when you take the metric in this form, you have like 1 minus m over r to the appropriate power. The m is the mass, which is the energy in the stress tensor. So, so you can do this for various quantities. Okay, but this is the particularly interesting one. If you have excited the bulk geometry away from ADS, well, if you're in pure ADS, the stress tensor is 0, as Roberto has explained very nicely. So I have there you have just the standard ADS, pure ADS geometry all the way through. If you, say, excite the geometry such that there is some additional, let's say, a black hole or something like that, or just an excitation, then in the bulk, it still can be a vacuum solution. The stress tensor in the bulk is 0, but on the boundary, that bulk as excitation sources a boundary, or induces a boundary stress tensor. So the boundary stress tensor is sort of a, gives you the fall off of the bulk geometry, and you can sort of try to expand in the Pfefferman-Graham expansion type thing of what's happening with the metric sort of inside the bulk. Okay, so I'm sort of saying this very schematically because I want to get to the more GRE stuff. So the main essence here is that we know how to relate the bulk geometry to some excited state, at least in characterizing it by expectation values of the various operators. Yeah. No. It's how the metric falls off radially. So like if you have the Schwarzschild metric in asymptotically flat space-time, and you want to relate the radial dependence of that metric to the ADM mass. The ADM mass is the coefficient of the 1 over R fall-off. Okay, so intuitively, this is just a generalization of that. Okay, there's a lot that I can say here. I just don't want to get bogged down in it because I wanted to move on to other stuff.
I mean, it's nowhere related to the Brownian spectrum.
Yeah. It's very much of what Roberto was explaining in the last lecture, at the last bit. Okay, so other questions? Okay, so good. So now let me quickly also talk about sort of causality. How do you see? Well, actually, I could have just. Well, let me just stay here with the picture. How does causality get manifested in between the bulk spacetime and boundary spacetime? So you might so on the boundary metric, the boundary metric is induced from the bulk metric, which means that if you have 2 points on the boundary that are time-like separated or causally separated on the boundary, then of course they're causally separated in the bulk because after all you could go arbitrarily close to the boundary, and because there's a time-like curve between them on the boundary, there's also a time-like curve between them in the bulk. The converse of that is not as obvious, so you might ask whether if you have, so suppose you're sort of space-like separated, but let me just catch up on what I just said. So time-like separated in boundary automatically means that it's time-like separated in bulk. Now, if your space-like separated points in the boundary, you might ask, does that mean that it has to necessarily be space-like separated likewise through the bulk? So after all, you might have said, well, it might be taking longer to go around the boundary than through the bulk. Are there sort of shortcuts through the bulk? And if we had just a cylinder in flat space, then that would definitely be the case because it does take longer to go around the rim of the cylinder than going through. But we saw that, well, these null geodesics, okay, this is one of the generators of the Poincare horizon, but that's a null geodesic. These null geodesics, in fact, all end up at the same boundary point from here. So even if you go, so if these 2 points are null separated along the boundary by this limiting geodesic, they also are null separated through the bulk, but this is for pure ADS. So you might ask, well, but what happens if you now deform from ADS as we were just talking about? Is it still the case that null geodesics that go through the bulk cannot emerge out sooner than the null geodesics that go around on the boundary? That would be a terrible problem because signals, the CFT is causal, so signals should not propagate faster than the speed of light in the field theory. But if they could do that in the bulk, well, in the bulk it would also propagate less than speed of light, but by the time it would get to the boundary, it would look like suddenly something happened acausally. Okay, so that would be a problem. So the fact that this does not happen, so indeed this is also space-like separated in bulk, is a statement of the Gauss-Walt theorem, which assumes, well, which uses the null energy condition and the genericity condition. And the intuition or the physics of it is very simple. If you do have, well, and Einstein's equations, okay. If you do have some physical matter that satisfies the null energy condition, then you just get a gravitational time delay. Okay, so what happens if you excite it, you put some stuff in the bulk, the boundary geodesics are not influenced by that, because after all, they're just on the boundary. It's infinitely far away from whatever stuff you put in the bulk. But the geodesics through the bulk get sort of delayed, gravitationally delayed by that stuff, and they actually come out later than the boundary ones, which is okay. So you have a slowdown of geodesics through the bulk. So in particular, if you have a space-like separated point here along the boundary, it has to be also space-like separated through the bulk. Okay, so that's one nice observation. But you might still worry that you can cook up, and this is what was done in sort of the early days, that you can still cook up some Gedanken experiment where you have a mismatch between what's happening in the ADS and what's happening in the CFT. After all, they're in different dimensions, so it feels weird that somehow the causality should really have carried through so seamlessly. So one of the very cute early day examples that really was done in the Lorentzian geometry was the following. Okay, so this was done by Gary Horowitz and Nissan Itzhaki in a very beautiful paper called something like shock waves and light cone states, causality in ADS CFT or something like that. And they set up the following thought experiment. So thought experiment. So, well, actually, they set up two thought experiments. One was to say, okay, suppose you have a particle that you throw in from the boundary, let's say particle A, and then later, from the same spot, from the same position, you throw another particle into the bulk. So this one falls in along almost null, or you can throw in massless particle along null trajectory. So does this one. And so that means, in particular, in the bulk, the later particle is always to the future of the first particle. So this presence of B cannot influence the evolution of what's happening with the particle A, right? Because it's to its future, so it's not going to do anything. On the other hand, on the boundary in the CFT, we had this intuition from the scale radius duality that, well, you have some excitation. So now let me draw evolution in time and space. I can even do this in just Poincare coordinates. Let's say this started at t equal to 0. So at t equals to 0, we had some localized excitation at the boundary. And now what's happening as time goes on, the particle gets deeper and deeper. So it looks like this excitation is getting smeared out more and more. So you would expect that what's happening with describing particle A is some excitation in the CFT that sort of grows like this. Now let me color code this, for the particle B, well, same thing happens just a little bit later. Okay, so then there is some excitation that looks like this. And it's absolutely not obvious why. Now you know, the orange thing is at the same place as the white thing, so it's absolutely not obvious why, from the boundary standpoint, why particle B could not influence particle A. Because after all, you have some dynamics happening in the strongly coupled field theory, and you know, they're happening at the same point. So what gives? So it looks like a blatant contradiction. Let me set up another Gedanken experiment and then give you a resolution on both of them. So you can also think of not throwing the particles in at different times, but throwing the particles in at the same time. And you can aim them, you know, roughly speaking, let's say this was still my particle A, and particle B you throw in from some other point, and they're roughly speaking going in, but they don't have to be aimed to be going precisely radially in, so they can easily sort of miss each other. And in the bulk, they don't need to particularly interact. Now in the CFT, again, we have the same picture. Now we have a particle A doing something like this, and particle B doing something like this. And no matter how I'm aiming this, it looks like after some time, which is just given by half of the separation here, there should be some strong interaction between the two particles. So again, it looks like we're getting something different in the dynamics between the bulk and the boundary. Okay, so that would have been, again, problem, instant shooting down of the correspondence. What we have not taken into account is doing this properly, doing back reaction of the particles on the geometry. So the CFT knows about the full physics of the bulk, and it doesn't separate things out in the same way as one might be tempted to separate things out in the bulk. It's just a different repackaging. And in particular, if we do things properly in the bulk, we recover exactly the same physics as in the CFT and vice versa. So in this case, what happens is that when these particles back react on the geometry, well, they're almost or exactly null. They create these so-called gravitational shock waves. So the metric, due to such a null particle, is really supported. It's pure ADS everywhere except for being supported on a transverse null plane, where the strength of the back reaction on pure ADS, diverges just along the particle, but falls off polynomial as you go away from the particle. Okay, so it's almost ADS, well, it's ADS asymptotically, of course, but it's pure ADS everywhere before and everywhere after the particle. So this is called the gravitational shock wave. You can write down the metric. The metric is sort of Eichelberg-Sechsel metric, and you can obtain it by actually taking a global ADS black hole and taking a limit and boosting it in ADS. So we start with a global ADS black hole, and we boost it. But at the same time, we take the limit of infinite boost such that the total energy is fixed. So if we boost it and preserve energy, we need to make it smaller. So we can boost it to a smaller black hole. Now it looks more like a particle. It's sloshing back and forth along almost a geodesic. If you take the limit of this all the way to infinite boost, the metric of this global Schwarzschild ADS black hole becomes limits to exactly this gravitational shock wave. Okay, so that's one way you can think about it. But according to our map there, that means that the stress tensor on the boundary is really supported only in the boundary region where there is no, where this gravitational shock wave reaches, where the metric deformation reaches. And so really, the picture here is something that's called a light cone state. So the stress tensor is really 0 everywhere before this particle. So this is stress tensor is 0 here, and it's 0 after. It's really only supported along the light cone. So that's why it's called the light cone state. And so we immediately see that if you have two of these light cone states, they don't interact because they're localized in different positions. On the other hand, so that resolves the first apparent paradox, because now it's consistent, the two particles indeed don't interact, and we understand that from both sides. But to understand what was happening here, we really utilized how do the particles back react on the bulk geometry. In this case, we also have these gravitational shock waves, so this is sort of making a shock wave that goes around sort of like this into the null surface starting from here. Okay, so it's like rotating this around, and here it's the same one. And now you can ask so now these shock waves do interact, they see each other. When do they see each other? They see each other precisely after the time that's given by half the separation, which is precisely what we are getting here, except here we also have these light cone states, but the light cone states now do interact at the same time. Okay, so this is one of the early lessons that, things work out after you sort of take into account the various relevant details. And if you have sort of an expansion of some quantity, the expansion, the individual terms in the expansion need not necessarily correspond to something natural on the other side, because after all, it was some unnatural expansion to start with, but the full thing, the full physics matches. Okay, there are many examples of that, which, at the beginning, you don't see how it could possibly work out consistently, and then it just falls out to sort of be this nice precise match. Okay, so any questions? Yeah.
So I get confused. So I thought we would make something going on in the bulk, right? In the first products, right? But in the end, we sort of made it look like nothing's happening on the boundary, so they do not interact. But I would expect like some, I don't know, like space-time to change in the bulk, and so that B and A would start interaction sort of in the bulk as particles.
For this one?
Yes.
Well, the space-time does change in the bulk. What happens is that you have one gravitational shock wave, so deformation from pure radius here, and you have another one above it, but both of those are parallel null planes. So because they're parallel, they don't run into each other.
Okay.
And in between, it's pure radius, and above and below, it's pure radius.
Okay.
So there is no, there's no interaction.
Okay, so then why not the sort of filled, sort of like the lumps of filled do not overlap on the boundary then? That's the picture I had in mind at least. So that, because I thought like we should the A particle, right, which corresponds to some lump of filled on the boundary, right, that some filled excitation, same for the B, and they would overlap in the boundary. Right?
Well, except that the metric of this really does not, so the state is going to be described, when it's moving in a null direction, it's going to be described by just this light cone state. If I took this and stopped it somewhere, or turned it to be time-like, well, first of all, the metric would be much more complicated now, but it would be the case that, or if I just hold a particle, let me take another one, I hold a particle, I accelerate the particle so that it just sits at some radial position. Can you see the blue?
Mm-hmm.
Okay, so at some radial position, that indeed would be some sort of a excitation that is filling out, you know, this whole thing.
Okay.
It's a light constant only because it's moving. It's really null. It's infinitely boosted.
I see. Okay, yeah. I am less confused now. Thank you.
Good.
So you're saying that the particles A and B are basically null trajectories, right? And they are producing shock waves that perturb the metric in the bulk? Is that correct?
Yes.
So I'm wondering, like, if you initially start to throw the particles from their initial point towards, inside the bulk, right? And the metric starts to perturb, how do you keep the null trajectories null? Because the metric starts to change perturbatively, right? Because of the shock waves?
Well, but so if I send a shock wave from some other direction, so here, the shock waves do, one perturbs the metric and the other one gets into that perturbed region, then then it ceases to be shock waves after that. Similarly here, after this interaction, this really is, we don't actually know, we don't have a precise form of the metric subsequently. You can solve it numerically and stuff, but, but it no longer has this nice pure form, but that happens on both sides again. Before they hit each other, right, both here and here, because the shock waves are propagating in pure ADS, they look like the single shock wave up till. It's like when you're patching GR solutions or something. You have an exact solution for a shock wave that doesn't know causally about the other one, that just localized somewhere else, until they meet, and once they meet, then the full nonlinearity of GR kicks in. You can't superpose these things in the subsequent evolution anymore. And, well, near the boundary you can, because near the boundary the excitation, as we said, dies off. You just do linearized GR and it's just superposition. But as you go into the bulk and you have the full nonlinearities of GR, then you have to solve for what happens. So we don't know what happens after these things collide, but we know that, well, the pictures are they're giving us the same physics. It just, we're no longer describing it in some closed form after the interaction.
And one more question regarding, once you start perturbing the metric due to the back reaction, is the null energy condition still valid for these null planes?
Yes. It's a vacuum solution, or rather the ICO blocks, it's a delta function source, and then the rest of it is just the black hole that's boosted, okay? It's a vacuum solution everywhere away from this particle source.
Thank you.
Good. So I don't mean to sort of dwell on the details of this. I just wanted to give you some illustrative example a little bit to just stress the point of things conspire to match, but along the way in the process as you're calculating the quantities, it need not be that something that was convenient on one side, expansion or breaking up one single physical answer is broken up in the same way on the other side. Okay, so that's one statement. Okay, let me now, so we have seen these special types of excitations. Let's now get to the more fun stuff, which is if you put in a generic type of excitation. So what happens on the two sides? So if you put in, so the dynamics, one obvious statement is the dynamics on both sides matches, the Hamiltonian matches, it's describing the same physics. So a process happening in the boundary has a avatar in what's happening in the bulk and vice versa. So you can ask, well, okay, so let me set up a dynamical process where we excite, we put some generic lump of matter in in the bulk. So dynamics matches. And if I put in generic excitation of large energy, meaning order n squared energy, let's start with order n squared times really factor that's larger than 1 in the ADS units. Excitation. In the bulk, maybe we should first talk about what happens on the boundary in the CFD. Okay, let's talk about what happens in the bulk. In the bulk, you have gravity, and of course, in flat space-time, things might disperse out to infinity, and or if you have enough of the matter, you have Jeans instability, and it's going to collapse into a black hole. In ADS, you still have all the gravitational attraction, but even more because you have this quadratic potential to draw everything in, as you can see by the geodesics, for example. And so you have, generically, this is going to collapse into a black hole. Now, what happens on the boundary? On the boundary, we don't have gravity, so we can't have black hole collapse. But we have strongly interacting field theory. And so any excitation you put in, generically, it's just going to thermalize. And it's going to thermalize on the same time scale as what's happening in the bulk of this black hole collapse. But in any case, if you wait until sort of large time, so at late times, which in case of black holes can be just comparable to the couple of times the light crossing time, because the black holes settle down very quickly, sort of again in this. But at sufficiently late times, you have a static. Well, you have a black hole, and it's described by a thermal state in the bulk. In fact, so if I did a sort of the picture from the collapse viewpoint, I would have started with pure ADS. I would have, let's say, some star or something, some stuff. It's going to sort of collapse, and okay, it will be singular here. And at the end of at late times, you have some black hole horizon. You continue the horizon back. It will have originated from somewhere, so it's not in this dynamical formulation, it's not an eternal black hole. But at late times, you can think of this bit as an eternal black hole, and so, in fact, this correspondence you can describe for an eternal black hole, as if you didn't create this, so I motivated this from the dynamics, but in fact, this also is actually much more precise for the eternal black hole. So the eternal black hole is the usual Schwarzschild radius. Is the metric that Roberto was writing down. Okay, it's still the same form as we had. Oh, did I erase it? I guess I erased it. Okay, so now, so it's a spherical black hole, a global ADS black hole, with this function being not just the ADS part, but then it has some, it has a horizon and it has a singularity. And that corresponds, so you can describe the thermal state in, so now, okay, I should still stay here. that now has not just a single asymptotic region. So here we had just a single asymptotic region. The Penrose diagram for this process would have been you start with this ADS. Let me just draw the origin, rho equal to 0 here, and scry here. And then in there you collapse a black hole. And so you make a singularity, you have a horizon, but there's just one asymptotic region. So it's like flat space, except now it's, the asymptotically flat case, except now it's asymptotically ADS. Here, similarly, it's like the Penrose diagram will be sort of like Schwarzschild. So let's start with Schwarzschild, and then in Schwarzschild, we would have had null boundary because it's asymptotically flat. But now, as you go towards large radius away from the horizon, the black hole now suddenly knows that, or the spacetime is now sensitive to the boundary conditions, knows that it's not in flat space, but in ADS space. And so you can take this part of Schwarzschild spacetime and interpolate to, if you take constant rho surfaces, at some point at large enough rho, you will hit this boundary, so it will no longer be null, but having this time-like boundary. Okay, so similarly here, now I have drawn in bent out like that. Usual way of drawing the boundaries is drawing them as straight. Okay, you still have the horizon, but you can conformally transform that back to draw the singularity as correspondingly bent. So if you had drawn three-dimensional BTZ black hole, the Penrose diagram really would be a square. But if you work it out carefully in higher dimensions, it turns out that, for example, if you shoot null geodesics such that they meet right at the boundary, right at the singularity, and shoot them from the same point into the path, they don't meet. And so it cannot be a square. So you can figure out how much, just do the proper transformation, conformal compactification to get a Penrose diagram. You find that, it happens that if you keep the boundary straight, the singularity has to be bent. Okay, that's just a curiosity. But anyway, so we have the Penrose diagram of the black hole with now two asymptotic regions and a past singularity and future singularity. But we know that the CFT, I have been saying the CFT lives on the boundary. Okay, it's sort of a misstatement because the CFT, it's not encoding just the boundary, it knows about the entire bulk. But from this UVIR perspective, it's a useful conceptual crutch to think of it that way. And so you might wonder, what do we do when we have two asymptotic regions? Well, what happens is that each one has a CFT associated with it. Okay, there are two completely distinct non-interacting CFTs. Okay, the boundaries are, of course, causally separated. You can't go from one to the other causally. So let me just label them as the left CFT and the right CFT to distinguish. And the bulk state for such a, the bulk connects up these two CFTs. So these two CFTs, even though they don't talk to each other, are collectively in a state that's in fact entangled between the two sides. So that's the so-called thermophile double state. Where you can take the full, the state in the collective one that describes this eternal black hole up to some normalization, you can think of as taking the energy eigenstates in the left CFT, taking a direct product with the eigenstates in the right CFT, with a factor that for a temperature T, which is 1 over beta, you have e to the minus beta EI over 2. sum over all the energy eigenstates. So you can write down, so this state is entangled between the two CFTs. So the CFTs don't interact, but they're entangled, and that entanglement, in some sense, gives rise to having a bulk spacetime that's connecting up the two boundaries. Okay, and this is something that has inspired Mark van Ramsdonk to sort of, and also Brian Swingle, to sort of propose that in some sense entanglement builds spacetime. Which initially is just motivated by saying, well, each of these energy eigenstates is just in one CFT, so what would it look like from the bulk? Well, maybe it looks like just, here you have one boundary, and maybe it's actually singular here or something. You have a product with the other CFT, which has some ADS geometry. Again, maybe it's kept off somewhere. They're completely disconnected. But when you sum over all of them, then you somehow suddenly create the horizon and the region inside the black hole and white hole. Conversely, if you start with this thermophile double state and you start disentangling the states from each other, you sort of create, you create an excitation that makes the horizon singular. You create a firewall, and the two sides sort of split up. Okay, so this is a very tantalizing statement because after all, we wanted to understand how spacetime, the bulk dynamical spacetime, classical spacetime emerges. And here we're saying, well, okay, it's somehow rooted maybe in something that has this entanglement structure. Okay, so what people have been doing in the past half a decade or something, or maybe already better part of the decade, was sort of trying to understand this statement in some, flesh this out to understand how precisely that happens, or even define what one means by, what aspect of entanglement is really responsible for this. How does one understand that? Okay, now, how much time do I have? Another 5 minutes. Good. Okay, let me pause for questions. I mean, if you start disentangling this, then yes, because after all, you're separating this out. But it's just you get a singular geometry, whether you want to put in the loaded word, a label firewall, then that sort of, there isn't a good definition of what one, different people mean different things by that. So it's a, yeah.
Thank you. I'm wondering about the general statement of this duality, because we are working like in ADS5 process 5 is dual to the inequality over your mills.
Yes.
But what is the generalization of this statement? For another kind of theories, which are in ADS also. What is the dynamics of the bulk theory?
Oh, so good. So
the dual of this.
Good. So maybe I can make few remarks, and then you can tell me whether I'm answering part of it and what else I should answer. But few pedagogical remarks that are worth saying is, first of all, the sphere. I haven't been mentioning the sphere. Here, I'm imagining, so this is really, the sphere is coming around for the right. So you have still a S5 with asymptotically ADS5. And that means the black hole is just smeared over the sphere. Now, if you take a small black hole in ADS, then it turns out that there is the same type of Gregory-Laflamme instability as Roberto was talking about yesterday. Yes. Now, instead of having just a black string that breaks up, you have a 5D black hole on this part, and instead of being smeared, it sort of localizes, so you have a 10-dimensional black hole that sits somewhere on the sphere. Okay, so once that happens, so further dynamics, if you collapse a small black hole, and by the way, that in the canonical ensemble, that was the unstable one, but in microcanonical ensemble, that is the dominant solution, so we're fine, we can be talking about small black holes. But if you collapsed one, then it would further destabilize once it's sufficiently small on the 5 sphere, and then you would have to take that physics into account. That's one remark, I should say. Another remark that Roberto already said, but it may be good to stress, is that already the global ADS-5 itself was extended from the Poincare patch. It's the global completion of the space-time. But what we got from the brane construction was just the Poincare patch. Now, we can get a black hole, a planar black hole in ADS directly by exciting the stack of these 3 branes. And as Roberto was saying, we can take a near horizon geometry of near extremal D3 branes. And that way we get a planar black hole. It's the same thing that would have been achieved by taking, the global ADS black hole, very, very large in the infinite limit of very large black hole, global black hole in ADS. It looks locally like a planar black hole. And so that's the one that we could get from the brane construction, but the actual global one, finite size global one, we can't get. But nevertheless, we still expect that everything, that ADS-CFT correspondence holds even in that regime. So we started in some regime, and now we've extended ADS to global ADS, and we say that CFT living on the Einstein static universe contains the physics happening in the full global ADS spacetime, whereas CFT that was living just on the, in the Minkowski spacetime described only the physics, up to these horizons, okay, in Poincare ADS. So because it's a CFT, so the construction gave us this bit, but we extended it, and then once we extend it, we can now do physics that we couldn't have done directly from the brane system. So that sort of feature keeps repeating itself at deeper and deeper levels. So now we can also extend the theories, and we can already have done something that went past the brane construction, but now we have this correspondence on the firm footing, and now we can deform that, and the deformations correspond, and we can keep going that way.
Okay. Thank you.
Okay, so I'll have the last lecture in the afternoon, and we'll continue from sort of this theme, but I'll try to bring it back to the GR stuff.